Yeah, let's have a wee practice. Please raise your hand if you have heard of blockchains. Okay, this is good. This is looking good. Phil Scott, please raise your hand. I know you've heard of it. Okay, 50%. You can put your hands down. Thank you. Now, who has heard of, who has an idea of the difference, hands up please, between accounts-based and UTxO-based blockchains? One person. Two people. Okay, you can put your hands down. Thank you very much. That felt great. I mean, I'm sitting here in a room talking to God knows what, so the more feedback, the better as far as I'm concerned. Oh yes, I've remembered the other thing, which is that I am giving this talk on a tablet machine, so it's difficult for me to type. By all means, send me private messages, but if I don't answer, I'm not being rude, I'm just fingerless, so to speak. Hands up if that's okay. Let's see some hands, please. Don't be shy. Oh, that's gratifying. Thank you, guys. Thank you. I feel validated, like I exist. You know, Ahad, what we need is a little smiley face so I know when my jokes hit home or not, as the case may be. Okay, so I'm going to talk about what a EUTxO blockchain is. Very briefly, there's two kinds of blockchains, account-based and EUTxO-based ones, and it's like two different species, like cats and dogs, and I'm just going to be talking about this particular type. I'd like to thank Ohad for the invitation to speak and the LFCS seminar series for having me. And also this talk is based on joint work with Lars Brunius. There's a paper online associated to this talk, and everything I'm going to say has actually been implemented in Haskell using the nominal data types package, and here are the links. Worry not, the slides for this talk are on my webpage, gabbay.org.uk, under talks, so you can pull the links and follow them straight off the internet right now. Indeed, you can also see the slides for this talk right now, if you like, so you can read ahead. You're very welcome to. Hands up if you're okay with all of that, please. Marvelous. Thank you very much. Okay, keep it coming with that hands up. It's the only feedback I have. I'm trying to change slide. Yeah, okay. So put it to you that this is what an idealization of what an EUTxO blockchain system is. So I'll call the solution to these type equations a model. I'll call the type equations idealized a UTxO, and I'll call a solution to them a model. I might also call it an algebra of chunks. So there you are. I will put my finger here so I feel like, there we are. So we have some equalities, we have some subsets. This is a list of transactions. I've borrowed Haskell notation. Now I think I'm going to go through this line by line in a minute. Yeah, so the only thing I'd note is you might be tempted to look at this blockchain line here, but I put it to you, you may be better off looking at this. And this is kind of a new idea, the idea of putting chunks first and blockchain second. So a chunk is just a certain list of transactions which, using this subset, we decide are good. And a warning that this figure does elide some details, and I'm just waiting for someone to stick up their hands and say, hey, yes, Jamie, but you forgot such and such, and that's fine. I have elided some things. The design philosophy with idealized EUTxO was to get it really small and compact, so here we are. Hands up if that's okay, please. Perfect. If anyone has a question now, please put your hand up now and ask. Then I will continue. Thank you. So an input is, oh yeah, so alpha is just a base data type for our blockchain. I don't really care what alpha is. We could take alpha to be the natural numbers. Of course, programmers care intensely what alpha is because it's the base data that our blockchain system is carrying. But if if you believe in Gödel encoding, if you believe that Gödel encoding has cost 0, then that is just fine. Atoms is secretly a Frankel-Masovsky style atom, and that's how it's implemented in the Haskell implementation. But for our purposes, it's just a countably infinite set of location identifiers. So if you want to find something on this blockchain, you have to know the position it's at, and that position is given by an atom. Any questions, just stick up your hand. Each input gets a unique identifier, as does each output. And by that I mean that we expect every input on the blockchain is in a distinct location, and every output is in a distinct location, but crucially, an input may have the same location as an output. And if an input and an output share a location, a common atom, then we say that the input points to the output. Are we cool so far? Hands up, please. Marvelous, thank you, thank you. Okay, so this is hopefully fairly simple. Yeah, so you might look at this, well, we'll come to that in a minute. So what is an input? Well, an input is just a piece of alpha, so it's a bit of data. And this data, you can think of it, I'm waving my hands around in the office right now. You can think of it as an alpha that's floating in space with an atom, a position attached so that you can find it. Like if you like a web page at a particular web address. If you know the position, you can locate the thing. If you don't know the position, you're out of luck. A validator is just a set of transactions. So a validator is a judgment about which transactions we decide are good. I'll come to that in a minute. Yeah, we expect validity to be computable, and this avoids cardinality issues. In practice, validators are defined by computer programs. So a validator is intended to be a little program which will input a transaction and output yes or no, depending on whether it likes that transaction. But for mathematical model, I'm just using the old mathematician's trick of identifying a function with a set. So an output is a validator that is located at a position so that an input can point to it. And a transaction is just a list of inputs followed by a list of outputs. And a chunk is a list of transactions. I should say that there are basic validity constraints that are imposed. For example, in the transaction, two outputs can't have the same position, two inputs can't have the same position, and in fact, also the positions of the inputs should be distinct from the positions of the outputs in a single transaction, which means that you can't have a loop. You can't have an input that points to an output in the same transaction. That's actually a design choice, and it's quite interesting to think of generalizations where you do allow loops, but I'm not allowing loops today. Any questions? Hands up if you have a question, please. Cool, okay.
Jamie Orestes has a question.
Oh, sorry, Orestes, I do apologize. It came up as a lower hand. Go ahead, fire away.
Hey, no worries. Isn't there another restriction in the transactions that the atoms are propagated from inputs to outputs? The
Very
alpha.
much. Yes. What do you mean?
So whatever A's you have, alphas you have in the input should be outputted as well.
Let's just go back to the, yeah, okay, this is the data type.
Oh, you're right. In the outputs, there is no alpha, actually. Yeah.
Right, okay, so if you go, the internet can go to slide 20 of the slides. In fact, I'll just answer your question right now. I'm trying, oh, this is so slow.
Jamie, could you post the link to your slides in the chat, perhaps?
Oh, okay. That's a very good point. I will go back.
You can go to, you can edit there's like a little navigation bar on the right you can use.
I can. Where is the navigation bar, please?
If you go to sharing, which slide do you want to go to? I can change that.
20. Slide 20, please.
Okay. There you go.
Perfect. So, Orestes, I suspect this is a picture you're thinking of, where outputs carry data as well. And for simplicity, I folded the beta into the validator.
Okay, yeah.
So there's a distinction here. Let me explain. If you care about efficiency, then your validators are created by scripts, and your inputs and your outputs both carry information so that they can kind of communicate and talk with each other. And the beta here tells the validator, in a sense, where it is. But mathematically, in terms of sets, all of these things are isomorphic. Does that help, Orestes?
Sounds good.
Marvelous, thank you. To slide 6, I'd appreciate it. Thank you. Perfect. Good, excellent. So to sum up, basically, implicit in Orestes' question, thank you very much, Jan. Thanks for the help. This is crap for programming. It's not designed directly for programming, but what I will say is that still there is a direct line from this to executable Haskell code. And I know this because I've done it. So it is there is operational content to this. Thank you. I will move on. And a chunk is a list of transactions subject to validity constraints. I've just compressed this down to 3 equations. So this is essentially the same of that. I've just folded it down a bit. And I'm trying to make a point here that this is terribly, terribly, terribly simple. This is, as far as I know, I'll stick my neck out and say this is the most compact presentation of the EUTxO idea in existence. So lucky you, here it is. Validity constraints on chunks are inputs must have unique positions. Outputs must have unique positions as outputs. An output can share a position with an input, but this must be a unique pair. An input can't point to 2 outputs, and an output can't be pointed to by 2 inputs. So graphically, it's a single link between a single input and a single output, and an input has to point to a previous output. Inputs aren't allowed to point forwards in time, they can only point backwards. And if we want to, we can alpha rename positions of output inputs pairs. That's in the paper. Oh, and yes, very importantly, if an input points to an output, then the output has to validate that input transaction. So an input can't just interface output just by knowing its position. It also has to be in a transaction that the output's validator will like and accept. And the analogy here, of course, is with a key in a lock. If I know where my next door neighbor's front door is located, but without the key, I can't get in. Any questions? Stick up your hand. I will otherwise continue. Well, the chunks are similar to a data type of abstract syntax with binding. They have notions of free inputs, which I will call UTXIs. They have notions of free outputs, which I didn't call them this, they're called UTxOs. And a blockchain is simply a chunk with no free inputs. It is left closed. I put it to you, though, that chunks are nicer than blockchains. They're nice objects to consider. For example, chunks form a partially ordered partial monoid. A monoid, you all know this, but I'll just run through it. A monoid is a thing with a composition and a unit. And here, an associative composition, I should say. Unit is the empty chunk, that's a chunk with no transactions. And composition is just list concatenation, and it's partial because not all chunks will fit together. The validators have to agree and the positions have to line up, and so on. So that's what makes it a partial monoid. And the partial ordering is very natural. It's just sublist inclusion. And it's just a fact that about validity constraints that if you have a valid chunk and you knock some transactions out, you still get a valid chunk. I'm going to make an observation. I didn't come up with the idea of chunks mathematically. I was writing the Haskell implementation, and in order to remove code duplication and get nice code, Haskell told me, I want a monoid structure, please. Basically, I was trying to operate on blockchain, but I needed to work with bits of blockchains, so these chunks. So it's interesting that the programming came first, even though this looks like something that a mathematician would have written, and indeed it is, but the impetus for doing so actually came from the programming, which I think is quite nice. Could you please reassure me that you and I exist? Please put up your hands if I can go to the next slide. Thank you. Thank you very much. Ohad, how's my pacing? Am I doing okay for pacing?
You're doing very well, I think. Thanks.
Thank you, darling. I appreciate that. Okay, so next slide. I don't remember writing this slide. Oh yes, so I'm going to go through a list of some of the simplifications I'm doing here. We're just talking about the structural aspects of blockchain. To be clear, there's a lot more to blockchains than this. The challenge of securing these structures cryptographically is just not considered in these slides. However, in my defense, at least conceptually, we provide a clean abstraction to which the crypto side can attach. I also want to say, it should be obvious, this talk is about a mathematical abstraction. Practical implementation is much more complex. However, I, for one, find these type equations and their algebraic structure brings clarity. And in fact, the reason I did this was because I was asking the question, what is an EUTxO blockchain? And this is the answer that I came up for myself. Even with all these simplifications, however, this talk does have operational content, and there is online right now. It's on GitHub. You should be able to find it. There are links. There's a Haskell implementation of the equations in this talk. So as much as there may be idealization here, there is still operational content. Ohad, did you have a question?
Yes. So you're using names here. So that means you're cutting out some symmetry, right? That will otherwise be muddling up the presentation. So is that improvement on existing presentations, or is that just something that you had at your fingertips and you just used?
Well, I did have it at my fingertips, of course, but actually it's necessary in the following sense. The existing presentations, it's a great question, thank you, Ohad. The existing presentations of EUTxO are inductively built as blockchains, so there's always a start, and locations are basically given by indexes that resemble de Bruijn indexes. So the whole thing feels like a giant, to me, feels like a giant de Bruijn system. And if you want to locate an input, you basically count along from the start of the chain. And it's the nth input from the start. Because of the theorems I wanted to prove and the things I wanted to do, I didn't want to always know where the start of the chain was. So I could not use, it's actually impossible to even express the theorems I wanted to express, which I'll come to in a couple of slides, using numerical indexes from the beginning, because there is no beginning. So to put this slightly crudely, perhaps, what the names give us is a clear view of chunks. Does that answer your question, Ohad?
Yes, thank you. Yeah, it's
Perfect.
yeah.
Now, in fact, in a couple of slides, we'll see the names giving us something more as well. Any more questions? I will proceed. What's original in this talk? Well, not the notion of an EUTxO blockchain. That's from the literature. And as I said, a whole line of inquiry came from me looking at the literature, asking myself, trying to develop my own understanding of what this stuff really is. The mathematical idealization, the idealized EUTxO, that is new. This emphasis on chunks and their partial monoid structure, and the minor but explicit idea of having a UTxI is new so far as I'm aware. And the idea of using names instead of numerical indexes and the symmetries that brings to the maths is new as far as I know. So let's use our maths. Basically, for the rest of the talk, I'm going to show you a couple of theorems, show you a couple of examples, and wrap up. So that's the rest of this talk. Let's look at the theorems, at some results we can take using this framework, this idealized and abstract framework. So any variable named will be a chunk, and I will write the free atoms of chunk for basically the locations in a chunk. So the free atoms of a chunk are the inputs that are free pointing left and the outputs that are free pointing right. There may be other atoms in the chunk, but they are involved in closed links, that is, inputs are pointing to outputs. And if you choose to, they could be alpha converted. And let's write that ch is apart from ch primed when they share no locations in common. I will put that there. So far, so innocent looking. Notice that being apartness is a really strong orthogonality assertion, and it has operational consequences. If the inputs and outputs of ch and ch primed can't connect, then they can't communicate, they can't compete for UTxOs or UTxIs of other chunks, so they are, if you like, occupying completely orthogonal information spaces, if you like, in the chunk and in any blockchain. Any questions on that? Cool, I will continue. Now, I said that composition of chunks is partial, and that's because if we want to bolt ch primed onto ch, then the validators on any, if ch primed has any inputs pointing to outputs located on ch, then the validators on ch have to agree that they'll accept these inputs. And furthermore, there can't be any name clash. For example, if ch has a free input pointing left located at A, and ch primed also has a free input located at A, then you cannot combine them because that's a name clash on the location, on the input location A, just as an example. So this is a non-trivial condition. If two chunks are apart, if they reference separate positions, then both compositions are necessarily defined because all of the validity constraints have to do with inputs and outputs interacting. If there's no interaction, then there can be no complaint. So this is kind of obvious. This is slightly harder to see, that if two chunks are can both be combined in any order, then they must reference separate spaces of positions. I'm not smart enough to see this immediately, but I believe it is true because, if you think about it, supposing we have an input here that points to an output there, right? Then if we swap it around, this would cause a complaint because input point to later outputs, right? Hands up if you see that. Okay, hands up if that's clear as mud. Philip, are you saying that that's okay? Sorry, guys. You really need to see a diagram, and I haven't conscientious enough to draw one. So I'll just run over this once more, and then I'll move hastily on. if you can see where I've put this little hand thing. Cool. Thank you. Okay, so let's suppose chunk primed has an input that is pulling information for an output in chunk. Okay? So let's look at this thing. This is chunk primed trying to compose with chunk, but now chunk primed has that input is trying to pull information from the chunk, but here the output in chunk is after the input in chunk primed. And it's just a rule that inputs can only reference previous information, not future information. So if you can build a link here, then that link would explode here because you'd have to travel into the future to reference the output. Sam, you had a question?
So I hadn't realized, but maybe it's kind of obvious, but there's a temporal order on this operator. The things to the left happen before the things further to the right.
Exactly.
Right?
Correct. Exactly. Thank you. So this temporal order is deceptively subtle here. This temporal order is that inputs here, if they point to something that happens here, then they're not allowed to point forwards to it. But if over here we have a situation where the things that happen in chunk and chunk primed are orthogonal, and then they are allowed to commute. So I'll sum up. Sorry, does that answer your question, Sam?
Absolutely.
Thank you. Thank you very much. So you may remember as undergraduates being in a lecture and everything the lecturer said seemed to be perfectly obvious, and then maybe your concentration breaks for a second and you look back and suddenly it's like he's talking Greek or another language or something. Well, this is where it happens. The maths is not difficult at all, but it just goes that extra step here. So it is a trivial but surprising fact that it's an if and only if, that this notion of apartness, which is very familiar from a non-context, coincides with an operational operational notion of happening in parallel. It sounds obvious when I say that, but it's not obvious until it's pointed out. So the deeper theorem here, which I never quite state in the slide, is that two chunks are apart from one another if and only if they commute up to observational equivalence. Instead, I'm going to state a different theorem. This theorem is in some sense the climax of my paper with Lars. I don't think, I'll be pleased if 50% of my audience get it right now, but the dedicated reader can read up on it at home. Oh, you are at home. Well, never mind. So supposing that all of these combinations are defined, okay, we have three chunks. And I invite you to think of CH as being a blockchain in its current state today. And we have a list of transactions which we wish to append to the blockchain. That's UTxO1. Hands up if we're cool so far, please. Marvelous, thank you. So this is the state of the blockchain now, and we've got chunk one and we want to append it to chunk. So we're really interested on whether that black dot is a valid proposition if we're allowed to append it. Now, there is a competitor out there with chunk 2, and our competitor wants to append his or her transactions to the blockchain as well. So we are in a time-critical solution. However, just so happens that we don't care even if our competitor appends their chunks to the blockchain, we can still append ours after. Then I put it to you that in this situation, it must be that chunk 1 and chunk 2 are apart and orthogonal. There is no input or output in chunk 1 that refers to anything that happens in chunk 2 or vice versa. Now, this might seem technical, but it's an important purity result, because what it's telling us is a really nice property of the UTxO system. If we try to attach a chunk to a blockchain, we will either succeed or fail. And because this is a distributed system, we cannot control what other chunks might get attached before ours. Even if we send our chunks off at the same time, even if I send my chunk 1 off before you send off your chunk 2, there's no knowing how the network will propagate the changes. So we have no control, but we know something. We know that the only thing competing chunks can cause us to do is to fail to attach. If we do attach, then there can be no competition with anybody else's additions to the blockchain before us. This is a bit like in functional programming. If you apply a function to an argument, it doesn't matter if somebody else's function got applied to another argument somewhere else first. It cannot affect the outcome locally for us. That's what this is expressing. And what's really potent about this is that this purity result that's encoded here is actually equivalent to a very abstract notion of name apartness. And this thing here, this lives in a completely abstract universe. It doesn't even know that the chunks are representing blockchain fragments or anything. Any question? Am I okay to move to the next slide, please? Hands up if it's okay. Thank you. And are there any, thank you. Are there any questions on this slide before I move on? Cool. Okay. So in a sense, this is a very full and complete answer to your question about what implicitly what names give us. Let's do an example. Let's fix alpha. So that's our data type to be natural numbers. And now we just need to choose some subsets. We need to choose what are our good sets of transactions, what transactions, what lists of inputs and lists of outputs we're going to admit, and what sets of chunks we like. So what I'm going to do is I'm going to do this. Don't panic. It's perfectly simple, I promise. So a transaction has to be a list of inputs and a list of outputs, and I'm just going to allow one input and one output, okay? And the input will be located at some p, and the output is located at some p primed. I have to give them positions because everything has a position, but the only thing I insist on is that their positions be distinct, because if p was equal to p primed, this could never be a well-formed transaction, because then it would be an input pointing to an output in the future. And for the record, I personally don't have a problem with that, but that's not how EUTxO systems, as currently conceived, are allowed. So that comes from the literature, and it's a, you know, it comes from, it's a time thing, Sam, that you were talking about. And a validator. And a validator is simply something that checks that the next output, the next input that tries to connect to this input, the next input that connects to this output should mention I plus 1. So if we think of this transaction as being the number I, then all it's saying is I'll connect to anything that points to p primed so long as it will say I plus 1 to me. So that's my little secret. And any input that wants to connect to me, any transaction that wants to bolt onto me has to know my secret, which is I plus 1. So this is a little challenge that says, can you calculate the successor of I? And we're just going to admit transactions that are these successor transactions. Are there any questions on that? Who's happy with this slide so far? Hands up, please. Thank you. Okay, that's good. So we admit any chunk provided that the positions match up and the validators are satisfied that, you know, we can calculate successors. And composition is list concatenation. The unit is the empty chunk. It's a very, very simple system. Ah, yes, James, please. What's your question? What's your question, James? Maybe your mic is muted.
So sorry, I didn't have a question. I just hit the wrong button.
Oh, okay, no problem. Nice to hear from you. Thank you, James. Okay, cool. So let's have a little proposition. There is a homomorphism of partial monoids from chunks to natural numbers given by mapping a chunk to its length as a transaction. The empty chunk maps to 0, and composition, attaching an n chunk to an n prime chunk, just maps to addition. So what we see here is that this system here, it's visibly, I mean, obviously counting. We see that right there. So this is the simplest example that I could think of a non-trivial system with non-trivial validators. And as I said actually before, the puzzle of bolting two transactions together is the puzzle of solving the successor operation. We note that this is a partial monoid, and actually naturals with addition is a total monoid, and that's okay because we expect partiality. That's the crypto part being reflected. So that the partiality here is just reflecting that blockchains are crypto flavored monoids. Now, this may seem like a, oh yes, of course. There's actually no blockchain in my previous example because I didn't give any facility. If I just go back 2 slides, every transaction has an input and an output. So you can't have what's called a genesis block, which is a transaction with no inputs. That actually doesn't bother me in the slightest because all modern systems allow users to download partial blockchains, but it's easily fixed. We just allow a 0 transaction, which is a transaction that asks if you can solve the puzzle of finding the number 0. So, you know, that's fine. Now, is this a simple example? Hell yes, it is. But I would like to put it to you that mathematically speaking, any more complex example is just a fancy pants version of what I've just shown. Now, this is not to say that blockchains are simple, they're not, nor that we have accounted for all complexity and dimensions. That's absolutely not the case. There's much, much more going on. But I put it to you that with idealized EUTxO, we've been able to simplify this complexity away. That's a feature, not a bug. We've abstracted detail, and this is, at least for me, a clear model with which to guide my understanding of what's going on in the fuller systems. Yes, Sam?
So you're describing EUTxO.
Yes.
What is UTxO? Or
fantastic question.
Obtain that by removing something from your system?
Absolutely, thank you. That's a fantastic question. So I'll answer that going to the next slide. Bitcoin is a UTxO system, and the UTxO, if we go here, can you see that where my hand is, Sam?
Yes.
Yeah. So with a UTxO system, the validator doesn't look at the whole transaction. It just looks at the input that calls the output. Let me expand on that. So a transaction is a list of inputs and a list of outputs, and an input can invoke a previous output, and that output has a validator, and the validator gets in a EUTxO system, it gets the whole transaction, in which the invoking input was embedded. In a UTxO system, the validator just ignores the whole transaction and just looks at the input which called that output. Does that make sense?
Yes. Thanks.
I'll use this perhaps slightly politically incorrect analogy here. If I call somebody up, then they might see my name flash up and they might say, okay, this is somebody called Jamie. Should I accept the call or not? But they might also see my area code and they might think, oh, Glasgow, that's a bit of a rough area. I'm not going to talk to anyone from Glasgow. And in the same way, with a UTxO system, there's a promise to only look at the purity of the input that called the output. But with an EUTxO system, you get a look at the company it keeps, which is a transaction the input is embedded in. And that gives a bit of extra power. Does that answer your question, Sam?
Yes, thanks.
Thank you very much. Great. Keep the questions coming. It's good. Now, one thing is that my previous type equations were aggressively simplified. It's not what you actually want to program with, and it's not actually what is implemented in the Haskell system. There's a very good reason for that. It's that computers are not good at representing arbitrary power sets. So if we want a function, then we write a piece of code. And that piece of code will take as an input, sorry, I forgot to say one thing. If you imagine a blockchain and you have some output that accepts an input, then you might want to propagate that output's validator to a new data state. So with this system, you can carry, the output can carry a data state beta around with it, and this output just operationally could propagate. If we imagine here this is time, so here the script in the validator can remain unchanged, but as state evolves, which is the beta, the validator will change because it has this extra parameter, which is the local state. I hope that makes some kind of sense. The bottom line is, if your validator is given to you as a script, then you'll need a little sort of parameter here to fine-tune the behavior of that script as that script propagates along along time and along the blockchain. Ohad, yes.
Are we ever going to consider infinite subsets? I mean, it sounds like effectivity is a red herring here.
Sorry, infinite subsets of what, please?
Is you know, you're taking a subset of the power set, but are you ever going to need something that's not the finite subset of?
Oh, definitely. Most validators, I would say, are infinite. In fact, well, I'm going to take a really
the class of sets is infinite. I believe that, but what I mean is, are there going to be elements in the validator that are infinite subsets?
Yes. Sorry, I'm not being clear. So your typical element, your typical validator is highly likely to be infinite. So let's take an example. Let's take a really simple, almost obnoxiously simple example. Consider typing your password in to log in, right? Even for this terrifically simple example, you might say, well, the validator is a finite set. It is literally single to that password, but it isn't, because you can press delete. So in fact, if we include the backspace character, there's an infinite number of admissible keys that will get you into the system.
Yes, but I only ever need to validate a finite sequence of them. So you know, whatever.
Can anyone in the audience give me with a concrete example of an infinite validator? Evidently not. Okay, fine. So I'm unable to produce a more convincing example, but I do believe that in practice, a validator may well be an infinite set of possible inputs. Still there?
I'm still there. It almost feels like we're talking at different levels. I agree that the validator can be an infinite set. I just think that the elements of the validator might not be infinite.
I understand. I will reaffirm. So an individual validator, which is a subset of beta, a specific set of transactions. In fact, I'm talking complete nonsense. So of course, let's suppose that we just want to look at one aspect of the transaction. So let's suppose we're just interested in whether the transaction, the input that called the output, has the number 2. So there's an infinite number of transactions with inputs that have the number 2, because there may be other inputs and other outputs that we're completely ignoring.
Yes.
So this is a concrete example of a specific validator that represents an infinite set of transactions.
Okay, maybe we can take it offline. Well,
Sure.
let me finish the talk, and then if there's time at the Q&A, we can discuss this further.
Okay, thank you very much. Hands up if I can continue, please. Marvelous, thank you. Thank you. Okay, so in fact, we are nearly done. In conclusion, we've seen a simple and abstract presentation of the EUTxO model and sketch its properties. I emphasize that chunks seem to be an algebraic structure. They are a partially ordered partial monoid. They exhibit name binding behavior, which corresponds to basically forming of graph links. And furthermore, this connection is not a superficial one, in the sense that key correctness theorems of the EUTxO framework correspond to name apart properties. So there's something more going on than just having names point to one another. Operational properties that programmers care about correspond to how these names interact. There's more to say that I haven't covered. And so there's a paper, there's a package, which I'd be delighted. Any feedback you have on either is most welcome. The paper is submitted for publication, so feedback now will enable it to be better. An example of future work would be to expand on the algebraic treatment of chunks. And this is what I'm working on now specifically. I've observed that a solution to the idealized EUTxO type equations forms a partially ordered partial monoid. What I haven't done is given you an abstract axiomatization such that every idealized EUTxO system corresponds precisely to partially ordered partial monoids with extra properties that identify the ones that look like EUTxO systems. And that's what I'm looking at the moment. So that would be called a universal algebra of chunks, if you like. Thank you very much. I'll hand over to you.
Okay, thanks. So we usually have a little round of applause in the chat. I don't know if you can see that, Jamie.
I can, it's lovely, thank you.
Okay, anyone has any more questions? We've had quite an interactive talk. Okay, oh yeah, Sam, go ahead.
So you say you implemented this in Haskell. Did this lead to any sort of practical outcomes or insights that you wouldn't otherwise have managed to do?
That's a great question, thank you. So let's be clear on what is a idealized EUTxO framework. So one practical thing, if you like, is a reference model for EUTxO systems. Right? So we go from I'm going to move my hand around. We go from the mathematical equations here to some Haskell code that kind of obviously implements it, and the theorems that we prove here become testable properties that we test in quick check. So it's really nice. There's a we're able to operationalize correctness theorems that are actually used to say, you know, this program makes sense because we know something's going to happen, is now cleanly stated in the maths and then tested in the reference implementation. I have hopes that people can then take this reference implementation, which is relatively compact, and use it to implement their favorite blockchain system. Blockchains aren't just about cryptocurrencies. They can be distributed ledgers, they can be state machines, and Lars is, as we speak, implementing various examples on top of the Haskell implementation. So that's where we're at the moment. To put it a slightly different way, you, Sam, if you wanted to, you could take the maths, you could take the reference implementation and say, okay, this is what I'm implementing, here's the maths, and here's my instantiated program doing a specific thing that I want, and we see how it all fits together. And I move this as a far clearer picture than existed before. Does that answer your question?
I think so, yes.
Okay. Any more questions?
So
Okay. Yes.
Orestes, go ahead.
Please, go ahead.
So you could say one of the novelties of your work is the addition of nominal treatment of the chunks instead of the Brown indexes, let's say. Now, I am working on formalizing this in type theory, and it's actually easier to work with the Brown indices. Now, is your nominal treatment necessary to use chunks like open blockchains, or is it something deeper?
So are you, Orestes, are you implementing complete blockchains or are you implementing chunks? Complete
blockchains. Not
so
implemented.
Yeah. Sorry, yes, I misspoke. So when you has a beginning, then it makes perfect sense to reference everything relative to that beginning. At least I started doing that, right? I started working with blockchains. In order to state and prove in the paper properties like this, and there's more in the paper. So this is situations where we're splitting a blockchain apart. So this EUTxO here, this could be a blockchain, but this EUTxO1 is definitely not going to be a blockchain in general. So it'll have dangling UTXIs. And I wanted to talk about how these things could commute. And then I'm not saying it would be impossible to talk about this with de Bruijn. You just get the usual thing about having to re-index your numbers. So right. One nice thing about using names is that if I have a system whose UTXI, whose positions are named, then I can pick it up, take it from here and move it to here, and the names don't change, right? Whereas if everything is indexed relative to its distance from the left-hand side of the page, and I pick something up and move it over there, then morally it hasn't changed, but in concrete technical terms, I need to insert a re-indexing. Right. That's where I was coming from. And then I'm still slightly flabbergasted by this, that there seems to be something else going on. I mean, initially I thought, yeah, I mean, I've saved myself having to work with re-indexing, but there seem to be mathematical properties that were of concrete interest to Lars that corresponded precisely to familiar things that I know from the nominal universe. That's where I'm coming from it, with it.
Great, thanks.
My pleasure, thank you. Anytime you want to discuss it offline, you're very welcome. James, yes.
Okay, yeah, I do actually have a question time. Now,
Hurrah.
now we're, I guess, talking about details of things. Is there a particular reason why you go for partial monoids rather than categories, or categories enriched in posets, or something like this?
Just for simplicity, basically, partial monoid was the structure that I needed to say what a chunk was. If I had many different kinds of chunks, then yeah, sure.
So I'm sorry, I'm thinking that the instead of saying, like, is there no way to characterize the appendability of these chunks as the objects of a category? This kind of standard
with structure. I have not considered this, and I would be happy to look into it further.
Yeah, I thought about mentioning it because there might be some more descriptions of structures on categories than partial monoids, you know, looking towards the things in your conclusion. But
yes, absolutely. Yeah, so I'm not thinking deeply here. I had certain things I wanted to say, and I pattern matched that on stuff from algebra. But what you're saying is there's a richer literature on categories, and yes, it might be possible to get a better match there. I'd be happy to share if you can see something that you like, then you can let me know.
yeah, I don't have anything in particular in mind. Other
well,
than,
thank you.
Yeah.
Thank you very much, James. Yotam, yes.
Hi. So just referring to what Ohad said earlier, I was thinking maybe an input that just needs to provide a secret to unlock an output, like a key.
Password.
Yeah, that'd be an infinite set because the input can then do anything it wants with the output it unlocked. So
yes, absolutely. So over here, a validator is a set of transactions, and a transaction will contain maybe an input that unlocks the output, but then it can have any other stuff here, including other inputs and outputs. So formally, a validator that just checks one aspect of an incoming transaction would be a infinite set.
okay, thank you.
Oh, thank you. I agree. Any other questions? Okay, can I just take this opportunity to thank you all for turning up? I'm delighted to have spoken with you, and if you want to discuss this with me further, then just drop me an email.